In section 6, chapter 6, we are going to study work energy equation again. If you remember from chapter 3, for a particle, it said whenever we have a particle that we are applying a force to it, like for example F, and this particle is moving on a path, then the work of that force on this particle, when this particle is moving, for example, from point 1 to point 2, it's going to be equal to work from 1 to 2. It's going to be integral of F dot dr. And dr, r shows the location of this particle, and dr means the movement in this on this path. So by integrating f dr, we are going to be able to find the work of this force. And also, we showed that if you consider all the forces that you are applying to the particle, then we are gonna have work energy equation between point 1 and point 2. So if you consider all the forces and calculate the work of them, at the end we came up with this equation: T1 plus V1 plus u prime from 1 to 2 is equal to T2 plus V2. And T1 is the kinetic energy of the particle at point 1. V1 is the potential energy of it. It can be gravitational potential energy or spring force, spring potential energy. U prime is the work of unconservative forces, like friction force or external force, anything like that. The work of them between 1 and 2. And T2, V2, they are kinetic and potential energy at point 2. We are going to have exactly the same thing for a rigid body, but it's going to have one more term on it. So on a rigid body, it is possible to apply a force, and it is possible to apply a moment or torque as well, right? So we need to calculate the work of the moment as well. So in the particle, the definition of work was F dot dr, but here the definition of the work is F dot dr plus moment times the angular displacement. So if this body rotates a little bit and the angle of it changes, the work of the moment is going to be moment times change in the angle. So we need to add this to the work as well. The rest of the thing is going to be exactly the same thing. So if this rigid body moves from point 1 to point 2, then we can use the Newton equation, work energy equation between these 2 points. T1 plus V1 plus U prime from 1 to 2 is equal to T2 plus V2. Kinetic potential energies at point 1 and point 2, and U prime is going to be the work of unconservative force and moments between 1 and 2. The other difference is for a particle, kinetic energy was 1/2 of mass times velocity squared. But here, the kinetic energy is going to have another term as well. So let's say the centroid of this rigid body, let's say it is here. It is not moving. If I keep this center fixed, then rotate this object, of course it's going to have some kinetic energy, right? But you are not going to see that kinetic energy in 1/2 of mv squared, because velocity of the centroid is equal to 0, right? So we can prove, actually the proof is in chapter 4, which is not in the syllabus, but we can prove the kinetic energy for a rigid body is equal to 1/2 of total mass of it times velocity of the centroid, let me call it Vg squared, plus 1/2 of I about the centroid times the angular velocity squared. So we have this additional term comparing to the kinetic energy of a particle. So we need to add this as well. And also, just one more point, we can show if we know the center of instantaneous center of rotation of a rigid body. Let's say, for example, we know velocity of 2 points of it, or the direction of that, and if we draw the perpendicular lines to those velocities, you know we can find this instantaneous center of rotation using this technique, right? Then, and also let's say it is rotating with angular velocity of omega. To calculate the kinetic energy, you can use this equation. This equation is always correct. But if you know where is C, sometimes it is better to use this equation. We can show this value, 1/2 of mass times velocity of the centroid squared plus 1/2 of I about the centroid times omega squared. It is equal to 1/2 of I, the mass moment of inertia of this rigid body, about C times omega squared. So combination of these two is equal to this. The proof is quite simple. I'll let you think about it, and also you can take a look at the book as well. And sometimes, actually, one specific case of this is sometimes we have a rigid body which is pinned to the ground. So whenever you have a rigid body which is pinned to the ground, the instantaneous center of rotation of it is going to be here all the time, right? Then the kinetic energy is going to be 1/2 of I about this point times omega squared. This is not anything different than this. But in this specific case, the instantaneous center of rotation is a fixed point. It is not changing all the time. But in general, the instantaneous center is not a fixed point. It can change all the time, right? So these are a quick overview of this technique, work energy equation. And I'm going to show how these equations work in practice. So just to recap, we are going to have exactly the same equation as we had for the particles. The only difference is going to be the kinetic energy. The kinetic energy, the general equation for it is this. We need to add 1/2 of Ig omega squared to it. And if we know where is the center of rotation, we can, instead of using this, sometimes it might be better to use this equation. We can calculate I about the center of rotation, then multiply to omega squared divided by 2. And one more point, when we are calculating potential energy, for example, if you want to calculate the potential energy of a rigid body, the equation was mgh, right? But h at what point? Whenever we have a rigid body, we need to calculate, we need to consider h of the centroid, which is trivial. So to show you in practice how these equations are useful, I'm going to do a few examples. This one, problem 89, chapter 6. We have this bar, which is stationary and this at this orientation. The mass is m, the total length is l, and we are releasing it from this condition. And the question is, what is the angular velocity and speed of the centroid of the bar when this bar becomes vertical? So the beginning position is this, let's call it 1, and the ending condition, or the second condition, is this. And the question is, what is the angular velocity at this moment? So you can solve this problem without using work energy equation. That's absolutely possible. But if you can use work energy equation, usually it is the simplest way to solve a problem. Because we are not dealing with accelerations, and also if you have a reaction force, Reaction force doesn't do any work, so we don't need to consider them. So it is usually much easier than simple Newton equations. So between 1 and 2, T1 plus V1 plus U prime from 1 to 2 is equal to T2 plus V2. What is T1? At the beginning, there is no velocity. So T1, the kinetic energy, is going to be equal to 0. What is V1? When we are talking about potential energy, gravitational potential energy, we need a reference line. And that reference line is going to be arbitrary. We can put it anywhere you want. Let's put it here, but we have to show it. This is my reference line. If this is my reference line, the potential energy at the beginning is equal to 0 because the height of the centroid is 0. Okay. U prime from 1 to 2. We need to see, do we have any unconservative force? We have gravitational force here, and also we have these reaction forces. Reaction forces are not conservative forces, of course, but they are not doing any work because they are not moving. So the work from 1 to 2 from unconservative forces is equal to 0. T2. To calculate the kinetic energy in the second condition, we can use half of mass times velocity of the centroid squared plus 1/2 of I about g omega squared, or because we know it is rotating about point O, we can say the kinetic energy is equal to 1/2 of mass moment of inertia about O times omega squared. But we need to calculate IO. IO is going to be equal to I about the centroid plus mass times distance squared based on parallel axis theorem. I about the centroid is 1/12 mass times length squared, and we need to add mass times distance squared, and the distance is L/4. So this is going to be IO. And the last thing we need to calculate is V2. What is the potential energy at the end? The centroid is going to be down here, and the height of it is going to be negative L/4. So the potential energy is going to be negative mg L/4. So if I put everything back in work energy equation, I'm going to have 0 plus 0 plus 0 is equal to T2, which is 1/2 of mass times L squared times 1/12 plus 1/16. This is nothing but IO. 1/2 of IO times omega squared minus mg L divided by 4. And if we simplify this equation, we are going to find omega. M is going to cancel out, and if you do the math, omega is going to be equal to square root of 24 times g divided by 7L. And of course, the direction of it is going to be clockwise. So this is omega, and if I want to find the velocity of the centroid is rotating about point O, right? So the velocity of it is going to be r times omega, and r is L/4. So it's going to be L/4 times omega, as simple as that. Let's do another one, another simple example, and use work energy equation. In this one, problem 19, I would suggest to think about it for 5 minutes. 5 minutes should be enough to solve this simple problem. Here we have this bar with the mass of m, and also we have this lumped mass 2m at this end of it. And we are releasing it from this condition, from rest. And the question is, what is the angular velocity of this bar when it rotates 180 degree, which means this 2m is going to come down, right? So the second condition, if I draw it here, just simply drawing this bar and also this mass on it, we are going to have angular velocity of omega here. So this is condition 1 and this is condition 2. So think about it and see the rest of the video after that. So between 1 and 2, I can again use work energy equation. T1 plus V1 plus U prime from 1 to 2 is equal to T2 plus V2. So let's put everything in the equation. At the beginning, there is no velocity. So T1 is going to be equal to 0 plus V1. If I put my reference line here, again, you can put it anywhere you want, but I'm going to put it here. The height of the bar, the centroid of it is going to be O, right? So potential energy for the bar itself is 0. Potential energy for this lump mass is going to be 2m times height of it, L over 2. So it's going to be 2mg times L over 2, or mg L. U prime from 1 to 2, the only unconservative force that we have is the reaction force at O, which they are not doing any work because they are not moving. So it is 0. It is equal to T2. T2, we can use 1/2 of IO times omega squared because we know O is the center of rotation for everything. So 1/2 of IO, I calculate IO later, times omega squared plus V2. Potential energy for the bar itself is 0, but for this one, because the height of it is going to be negative L over 2, the potential energy for this one is going to be negative 2mg times L over 2, or negative mg L. And from here, we can find omega squared if I know what is IO. So we need to calculate IO. What is IO? I has two parts. For the bar itself, of course, I about O is going to be 1 over 12, mass of it times length of it squared. For this lumped mass, it's going to be the mass times distance from O squared, right? So it's going to be 2m times L over 2 squared. So this is going to be I of the whole system about O. If you put this here and simplify everything, you're going to find omega. Omega is going to be equal to the square root of 48 times G divided by 7L.